Yeah, now Guhan, you can start.
Okay. So welcome everyone for week 6 of this wonderful trimester program at Bhaskaracharya. It gives me immense pleasure to introduce Professor Raghuram from Fordham University in New York, and he'll continue his seminar series on Hilbert modular forms. So over to you, Raghuram.
Okay, thank you. Thanks for the introduction, and it's kind of a special pleasure to get introduced by one of our former students. Guhan, many of you would know, is from one of the early batches of IISER Pune, and now his faculty. So it's kind of like a major success story for the IISER Pune in particular, and the IISER model of education in India in general. So thanks, Guhan. Okay, so let's get to work. I was talking about Hilbert modular forms. And let me just very quickly recap where we were. So this first page here is in some sense, I often, if you have heard me give talks before, I often try to organize my own thoughts through this kind of, some diagram of this kind, a flowchart, if you will, connecting broad sort of passages or clusters or circles of ideas. So to get some notation in place, F is a totally real field, D the degree of F. And I'm just going to quickly go through this. You take the embeddings of F into complex numbers, and F being totally real, that's the same as embeddings of F into R, which I index as tau1, tau2 to tau D. OF is the ring of integers. Frac N is an integral ideal. And we take a weight, which is a bunch of integers. So all this K1 through KD is each Ki is integer, and I'm going to assume all of them is bigger than or equal to 1. You take a Dirichlet character of the totally real field F, which is a character of OF mod N and its group of units, and I can idealize that omega and call that omega tilde. Now, one is the classical world of Hilbert modular forms, which is the space of weight K, level N, Nebentupus omega tilde, space of Hilbert modular forms, cuspidal Hilbert modular forms. And we impose some conditions that it's eigenform, it normalized in some way, and it's a new form, doesn't come from smaller levels. And this reference of Shimura is really, I really love this reference. This paper in Duke in 1978, where in just some 5 to 10 pages, it really summarizes, in some sense, all the basics that you will need to know to get started. I don't know if I mentioned this other reference. By the way, I'm happy to share these notes at the end of my talk, which will have notes of both these talks. The other reference is, I like this book by Paul Garrett. If you can lay your hands on this, it's unfortunately out of print. I got a photocopy. It's simply called Holomorphic Hilbert modular forms. So there's a certain classical world, and then one can think of this via representations. I guess this bijection here goes back to 1950s in the context of F equals Q. Already by the early 1960s, there's this book of Gelfand-Graeve and Pierre-Shapiro, where this connection between modular forms and representations were in place. And I know that it goes back earlier. I would like to say the Gelfand school, where you can talk about cuspidal automorphic representations of the adelic group GL2 of AF. And such a representation, this is an adel. Adels is a product of completions, and GL2 of adels is product of GL2 of all the completions. And so an irreducible representation of the adelic group is a tensor product of irreducible representations, but it's an infinite tensor product, and you have to make sense of this. Almost all places you actually fix a vector, and then the other places, finitely many places, you can let things be arbitrary. And for this representation to correspond to a Hilbert modular form, this at infinity, you want these to be a tensor product of discrete series representations. And I gave a quick kind of glimpse into these discrete series representations last time. And today, really, I want to talk about how these kind of representations contributes to the cohomology of GL2. loosely speaking. A little more technically, the cohomology of a locally symmetric space of GL2 over a totally real field with coefficients in some sheaf. So this is the agenda for today. This is what I want to talk about today. And once this is in place, time permitting, we'll talk about L-functions and how to view L-functions in cohomology. Okay. And now if you didn't want to go through automorphic representations and want to directly connect the classical world of Hilbert modular forms to this geometric world of cohomology of arithmetic groups, this vertical arrow here, this is what is classically called the Eichler-Shimura isomorphism. Okay. So I will make, maybe I should remember, I would like to make some comments about that a little later. So this is an overall picture of what I'm discussing in these two courses, in this mini course of 2 lectures. Now, quick recap into notations. You want to work in the general framework for Hilbert modular forms, and for that you need to worry about the narrow class group. And the reason is this exercise here, that if I look at GL2AF and I go, so on the left, mod GL2 of the principal ideals F, and on the right I go mod maximal compact and and some open compact subgroup, the level structure. Then this is represented by elements in the narrow class group. Okay. And let me just remind you of this picture here. On the left is the space of adelic Hilbert modular cusp forms, and on the right, on each connected component, it feels like a classical world of you take a product of upper half planes, d many copies, and then I go modulo a discrete subgroup, this discrete subgroup, and just drawing line by line parallel to the classical world of elliptic modular forms. Where you do upper half plane mod a discrete subgroup. Here I have a product of upper half planes, and this discrete subgroup kind of acts on that product in some diagonal way. And then you write down a definition of cusp forms there. Or it's better to work adelically, because these connected components, these different connected components kind of get moved around adelically. Okay. So the space you want to consider is not just one connected component, but actually all of it together to play any kind of a global game. So that's the left-hand side with this boldface F standing for a Hilbert modular form in the adelic world. All right. And then I talked about Fourier coefficients. And then this was a very, very quick glimpse into automorphic representations. You want to make peace with this world of automorphic functions, which are functions on GA mod GF, and it's a very technical definition. Let's just say, reasonably smooth in some sense, functions with some reasonable growth properties. Okay, so some good-looking space of functions on a space like upper half plane mod gamma, except we are talking adelically. And inside that is lives the space of cusp forms, which is the analog of the zeroth Fourier coefficient being 0. Or you can fix a central character and talk about the same spaces, and technically it's always better to have fixed a central character. And the reason is this the underlying locally symmetric space, which I'm using in a loose way, not as a differential geometer would use, but simply as a GA mod GF mod something at infinite, mod some compact. I want that space to have finite volume. Okay, so to have finite volume, I want to just cut out the center. So you want to have either say it's mod center or put a central character. So this is always a useful technical artifice, simply to make my underlying space on which all the action is happening to have finite volume. And a basic theorem here, which is that the space of cusp forms is a direct sum of irreducible representations of the adelic group, and these are called cuspidal automorphic representations. That it's a direct sum is just pure functional analysis. Again, I think goes back to, I would like to say the Gelfand school again, Gelfand and Piagetski Shapiro. I could be wrong on those historical details, but in some neighborhood of that, I think that's correct. And this, given a classical Hilbert modular form thought of adelically as a function on GA, this generates, it's some function, one element in this function space, and then I can look at the orbit, the GA span of this function, or the span of the GA orbit of this function, and that in fact is an irreducible representation. That needs a proof. This is considered standard in this part of the dictionary. So here, you want to go from, oh, I see that my screen scrolls kind of slowly there. In that bijection between, in the classical world of modular forms to automorphic representations, this needs work. It's not obvious, okay? But it's now considered standard material. For F equals Q, there's a good reference, maybe for students or anyone who wants to read these things up. There's a book by Steve Gelbart in the Annals of Math Studies. This is, I think it's called Automorphic Forms on Adele Groups, where there's a systematic treatment of, given a holomorphic elliptic cuspidal modular form of some level and some Leibniz, how do I get that irreducible representation? And the corresponding story for Hilbert modular forms is all kind of known to experts. My paper with Naomi Tanabe has all the relevant details, or enough details for you to understand the story, if not all details. And then I talked about the representation at infinity being a discrete series representation. And here was a quick construction. What I want you to recall, especially for just to kind of move forward here, is these discrete series representations sit in a short exact sequence almost by construction. Mu is I'm working with the group GL2 over R. This is the highest weight. It's just a pair of integers A and B. And for this to be dominant, if I fix the choice of Borel as upper triangulars, I would require A is bigger than or equal to B, this condition here. And for a dominant integral weight, there's a finite dimensional irreducible representation with that as the highest weight. That's my representation mu. And you have to work through the GL2 theory to realize that this mu is nothing but the A minus Bth symmetric power of the standard representation, twisted by some power of the determinant. And so this discrete series representation sits in this short exact sequence, which does not split. The discrete series is one irreducible subquotient, and this finite dimensional is the other irreducible subquotient. And you can arrange your inducing data such that the discrete series is the sub and the finite dimensional is the quotient. And since this sequence doesn't split in some suitable category of modules, I get a element in, I'm here now, I get an element in X1 between those two modules. And then you can play a game of pushing one of the modules across the comma sign. You can do it for finite dimensional. This gives me a class in X1 between the trivial representation and that tensor product of discrete series and the dual of the finite dimensional, just another finite dimensional. And that by definition is the first GK cohomology. So the appropriate category of modules is the category of modules where the Lie algebra G and the maximal compact K act in some compatible way. In that category of modules, it's an abelian category. I can talk about this GK cohomology. I will talk a little more about GK cohomology a bit later. So this is how this discrete series representation contributes to cohomology. This statement, these are the underlying details. And if I take this classical Hilbert modular form of weight K, which is K1, K through to KD. Oh, part of the screen is cut off on my laptop. You don't see the pi infinity is.
I can see this actually.
Oh, you can see it, is it?
Yeah.
Only on my screen it is. Maybe if I make it full screen. Okay, no. I see. Anyway, so there is a line, maybe you see it, maybe you don't, over here, that the maybe I can just,
push
if
the
you
computer.
cannot see it. The pi infinity, I'm just going to, this is what I wanted to talk about. The representation at infinity is a tensor product of certain discrete series representations dictated by the weight of that Hilbert modular form. Okay, so much was what I talked about last time, and then I want to get into how we talk about cohomology of how we put a cohomological context. Now we get into today's talk. I've already blown 17 minutes in just reviewing. Okay, so let me set up my notations somewhat carefully. I'm going to take G to be the G to be the restriction of scalars from F to Q of the algebraic group GL2 over F. This is again just a technical artifice. Some people prefer to work with a Q group, some people prefer to work, or it's I'm going to let KF stand for an open compact subgroup of G of AF. A sub F is the addels of Q, the finite part thereof. And by definition of this restriction of scalars business, this is the same as GL2 of the, with points in the finite part of the addels of the field, number field F. I'm going to let G infinity stand for the group, the Archimedean, the R points of the group, which is by definition of restriction of scalars. This is the same as GL2 of F tensor R. And this is the product of over all the Archimedean places, GL2R. C infinity is going to be a maximal compact subgroup, maximal compact in G infinity. So that is just the product over all the Archimedean places. The maximal compact subgroup of GL2R is O2. And now I told you it's always good to cut out by the center to make something of finite volume, the space over which all the action is going to happen is to have finite volume. So I'm going to take Z to be the restriction of scalars from F to Q. Of the center, I'll just call it Z2 of F. So Z2 is simply the center of GL2. The scalar matrices, okay, that's Z2. And then I take the restriction of scalars. So this is really, Z2 is just a copy of GM, yeah, the multiplicative group. Now this is a Q group, and I'm taking a restriction of scalars. In this sits over Q, a copy of GM. Some kind of, I don't know what to call this, a little bit of Frobenius reciprocity like feel to this. It's like the Z is, for every place there is a scalars, and then I'm looking at a diagonal, and AA sitting as AA, like that. It's the center of the center, so to speak, sitting diagonally in this product. So that's and that's rational. So that's, I'm going to call that as S. And I'm going to take K infinity to be my maximal compact, slightly thickened by this S, the real points of S. So that's just one copy of R cross. Okay. And K infinity circle is, for any topological group, if I put a circle on top, this is just the connected component of identity. Okay. And my space over which all the action is going to happen, I'm going to denote this SGKF. This is GA mod GQ mod K infinity circle KF. This KF, I didn't, maybe I said this without writing, this is an open compact subgroup. It's like that, for example, it could be the K0 of frac N, the Hecke congruence subgroup we considered earlier. And now you want to sort of parse this a little and ask yourself, what kind of space is this? So this is GQ is nothing but GL2F. GA is nothing but GL2AF. And the compacts are still as they are. Or maybe I can say something about K infinity circle. K infinity circle is, well, the SR is just non-zero positive real numbers. And for every Archimedean place, I'm looking at SO2 in O2. That's the connected component. So this product here is the connected component K infinity circle, and this times KF. And this equals, and there's a little bit of thinking to do here, the disjoint union over nu. Nu, remember, is my letter parameterizing elements in this narrow class group. So this, a certain discrete subgroup gamma sub nu of the product of GL2 or this product's running over Archimedean places, positive determinants, and I cut out all the central point, beg your pardon, the compacts. This is like my upper half plane, except there's a little bit of extra center to worry about. And I think I should throw in my R cross plus. I hope this is correct, or something very close to this. If not, this might be okay. So this is my the connected components in some sense is what I just described. It's like the product of the upper half planes modulo a discrete subgroup. You can think of this gamma nu as, the largest it can be is roughly like GL2O or SL2O, if O is the ring of integers of that base field. And this is again equals up to maybe it's a little bit of thinking and a little bit of fudging, gamma nu and the product of upper half planes. I'm fudging a little with that center. So don't worry about the center part. It's in any case, that center, as long as you keep in mind that I need to cut out something in the center to make the space to have finite volume. That's the role that center is playing. This is what I will loosely call a locally symmetric space. If Ravi Kulkarni is going to allow me such differential geometric blasphemy, because differential geometers are very careful with what would constitute a locally symmetric space. But this is loosely speaking. You have to worry about this open compact needs to act. You see my space HD, that is, that's simply connected. I can just homologic to a point. So I'm going mod some discrete subgroup. Now for this to be a covering map, I want this discrete subgroup, I shouldn't have torsion elements. So that I can always arrange by shrinking my KF to have the deeper KF in finite index in any given KF, so that none of the gamma nus have torsion. Sometimes these people call such a thing, so I'm going to assume what I just said is assume KF to be neat. I just gave you a definition of what neat is. Neat is all the relevant discrete subgroups gamma nu shouldn't have torsion elements. Anyway, so I can consider this space purely as a topological space, and now I'm going to construct a sheaf on this space. Towards that, I take T to be the restriction of scalars from F to Q of the torus T2 in GL2. T2 is just all diagonal elements in GL2. And I'm going to take mu to stand for a weight of T, which is a Q group. And I'm going to base change this to complex numbers. Now, in my work with Harder and starting from there and many other of my recent papers, you will see this base change not happening to complex numbers, but base change to some other number field E. To play an arithmetic game, you want to just base change to some arbitrary field and see how everything behaves upon changing that field of coefficients. In this kind of a talk, I don't have the time, or I don't really have the time to develop that systematically. So I'm just going to base change to complex numbers. For example, for those of you, people like Guhan are interested in p-adic interpolation. this E can be a number field, and then I can further base change to some periodic completion of E, and then set things up so that I can play some periodic interpolation game. Anyway, so I take this, and so what is this? What does such a mu look like? So this mu is itself parameterized as a tuple mu tau, where tau runs over embeddings from F to C, and each mu tau is a weight of this T2, which is an F group I base change via tau to C, but that's split. So any base change continues to be split. Mu tau is just two numbers. I'll call this mu tau 1, mu tau 2, two integers. Is that too small? Can you see?
Yeah,
You
I
could
can
zoom
see.
in the screen little bit somehow.
Can I zoom in the screen? How do I make this?
By fingers.
Yeah, yeah.
And so this is a element of Z2. This is like the A comma B. When I talked about discrete series, I was just looking at one weight. Now I have one weight for every embedding of F to C. And then if I have to do this pinching game, I need another page. I'm going to let mu stand for the finite dimensional. If I had a coefficient field E, I would say absolutely irreducible, but here I'm over complex numbers, just an irreducible representation of the algebraic group. G was a Q group, and now I base change to C, so I might as well do G cross C. So what is this? This looks like the tensor product over tau, m mu tau, and each m mu tau is that mu tau 1 minus mu tau 2th symmetric of the standard representation twisted by the determinant of, if I remember correctly, it's a mu tau 2. Okay, some GL2 theory. Okay, don't worry too much about that. The point is, it's a standard, very well-known finite dimensional representation of the irreducible representation of GL2C, and I have one such representation for each Archimedean embedding. This mu gives me a sheaf. Mu tilde is the sheaf on the locally symmetric space SGKF. And this I want to explain. If you have seen this, very good. If not, you have to see this once in your life. So where's my space? SGKF is here, which is my locally symmetric space GA mod GQ mod K infinity circle KF. And this, I want you to think of as roughly the connected components, roughly having the shape product of upper half planes mod some discrete subgroup. I take the covering map HD to HD mod gamma, and here adelically I'm looking at, I just don't go mod the discrete subgroup GQ. So I look at GA mod K infinity circle KF. Let me just tentatively call this map, this vibration as pi. And I want a sheaf on the space. What is a sheaf? Well, since I'm going to associate the sheaf to a complex vector space, this is going to be a sheaf of complex vector spaces. What is a sheaf? For every open set, you want sections over that open set. So I take an open set U here. And the sheaf, the sections of the sheaf over this open set consists of the set of all functions S from pi inverse U. So I pull back U, it's like various, that's a covering map there. So I got various disjoint unions of U mapping to the representation space MUC. But this disjoint union of U's is kind of moved around by the action of GQ. And this GQ action you want to bring in here. S of gamma NEX is, let me call this representation as, call this representation rho mu mu. See, okay. Rho mu stands for the action on that vector space mu. So this will be rho mu of gamma S of X. What kind of functions S we allow is, let me just gloss over such points. But this is the bare bones construction of, this is a sheaf of complex vector spaces. Well, at least I've given you a candidate for sections over an open set. And then you want to sit down and check your sheaf axioms that if I have some section, some local sections which patch well, then there's a unique global section which restricts to those local sections. You want to check that. And now there's an interesting point, which is even if my irreducible representation mu is an honest to goodness irreducible representation, the sheaf need not be non-trivial. So it is possible that for the sheaf to be 0, okay? So, and then you want to, there's an easy lemma to prove that the sheaf is not 0 if and only if it's some compatibility of the weights for the different embeddings. Mu tau 1 plus mu tau 2 is a constant. I'll just denote it W for every tau. Okay, so this kind of a condition later plays a role. It's called it's a certain kind of purity condition on my highest weight. And this numerology plays some role when you want to play some role if you really want to do some calculations. And the main object of interest in this cohomological game is this sheaf cohomology group H dot, this locally symmetric space with coefficients in the sheaf. And under the condition that the sheaf is not 0, and under the condition that my KF open compact is small enough such that it's actually a covering map, then the stock over every point can all be identified with the same vector space mu. And this such an object is also called a local system. And you will see people use the phrase cohomology of arithmetic groups. And while talking about this, you may not even see an arithmetic group, and it's kind of there behind everything. Because if I think of this roughly as, if I were to look just at one of those connected components and look at the restriction of the sheaf on that connected component, this, if it's actually a covering map, this sheaf cohomology group can be is isomorphic to the group cohomology of that discrete subgroup with coefficients in that vector space mu on which it acts. Okay, and this right-hand side is the cohomology of the arithmetic group gamma nu, and hence the name of the subject. Okay, this so far was just setting up my context, and now what? Any questions so far? Because I will be kind of, as I get deeper into my talk, it is going to get a little more complicated.
Just a small thing, like I think in between from where we describe the map S from pulling pi inverse U by this, there's somewhere some compactification also required, right? Like probably to
not yet.
Not okay. Yet.
Not yet. You can compactify. There are the space, as Jitendra is pointing out implicitly by his comment, the space, locally symmetric space, like the upper half plane modulo SL2Z, this is not compact. I can take off to infinity. And there are various compactifications. There is a plethora of compactifications. In the work with Harder, based on previous works of Harder, the Borel-Serre compactification has played a role. If I want to understand these cohomology groups, once I have some kind of compactification, then you take the topological pair, the compactified manifold, comma, the boundary that you have attached to compactify. So once I have a topological pair X comma A, I have some long exact sequence in homology, cohomology, whatever. And so that gives me a certain long exact sequence in cohomology. And all these sheaves can be extended to the compactification, to the boundary, everything works very well. There's a certain long exact sequence. That sequence is one of the fundamental tools to understand these objects. But just to define this object, I don't need the compactification.
Okay, yeah, thanks.
Any other questions? Okay, if not, I move on. So where am I in my notes? Now I would like to relate this. So this is maybe my next section. There is a theorem, and in some sense, one has to make one's peace with this theorem. It takes a while to, sort of absorb the details to even appreciate this, but this is kind of fundamental for the rest of the game. We have this cohomology of this locally symmetric space with coefficients in the sheaf. How do I understand this cohomology group? So you got to go back to, I'm going to fill in something here. I'm going to say this is isomorphic to something or the other, but what is this? This is sheaf cohomology. What is sheaf cohomology? Well, I have some category of sheaves on some space X, and maybe I take the globe, or maybe I take the global sections functor. If I have a sheaf F, I take its global sections. And if I'm looking at sheaf of abelian groups, I go to abelian, the category of abelian groups. And then this is a left exact functor, and then you take its derived functors. This is a crash course in sheaf cohomology, the 3-line crash course. So the cohomology of X with coefficients in F are the derived functors of the global sections is also denoted H0. Yeah. And the derived functors applied to F. Now, this is not so helpful. And now you want to, how do you compute these kind of cohomology groups? You take a resolution of the sheaf, you take the sheaf, and then you put it inside some resolution, I0, I1, I2, some injective resolution. Now, then you realize that you can work with some acyclic resolution. And then you have a choice, and the cohomology groups are independent of the choice of resolution, blah, blah, blah. All that has to be developed. One particular resolution relevant to the game is I can work with the underlying space is little more than a topological space. It's a manifold. I'm assuming there's no pinching. If there's pinching as an orbifold, forget the pinching. It's a smooth manifold. And I can look at the Durham resolution. For every open set, you look at differential p-forms on that open set, and that gives me the sheaf of p-forms. And I can tensor it up by F, and that gives me a certain resolution of F. That's the so-called Durham resolution. We keep that in mind, okay? And now I'm going to jump across this isomorphism. On the other side, this is isomorphic to, I'll just write this out first, the GK cohomology, and I'm a little careful in my notations now, G infinity, K infinity cohomology, K infinity circle cohomology of the space of smooth functions on GA mod GQ. And since I had a level structure, I have to take invariants, KF invariant functions tensored by the representation space MU. The right-hand side is what's called relative Lie algebra cohomology. How does that work? Well, I got some Lie algebra suppressing all the infinity and the circle. I have a Lie algebra, reductive Lie algebra maybe, and a maximal compact subgroup of the ambient reductive group whose Lie algebra is G. Both of these could act in a compatible way, and that's the category of GK modules. And from this category of GK modules, I can look at the functor to vector spaces by taking a GK module, and like what you do with group cohomology or any of these cohomology theories, you take invariants. I look at H0 GK V. So this is H0 GK V is all those vectors which are killed by everything in the Lie algebra and fixed by everything in the maximal compact. Okay. Taking invariants under the group, what you do with groups, now you do that for the compact group K, and for the Lie algebra, fixing becomes killing. And again, this is a left exact functor. You take its derived functors and you get the corresponding, the cohomology theory is called relative Lie algebra cohomology. To see the relation between these two, there is one can identify, again, by choosing one of your resolutions to compute that cohomology group carefully, one can identify the relative Lie algebra cohomology as the cohomology of a certain complex. The complex is given as Hom. Maybe I need more space here. Let me just do it here. K equivariant maps of wedge products of the Lie algebra G mod the Lie algebra K, on which capital K acts via adjoint, and it also acts on the representation space V. And then there's a certain complex I can cook up like this. And it's a fact that the cohomology it computes is the relative Lie algebra. This can even be one definition of relative Lie algebra cohomology. And then the point that you want to hold on to your thoughts as an anchor to go between the two sides of this isomorphism lives there. This G mod K is, what is this after all? This is the tangent space at identity of the group of real points mod that maximal compact. So that's what it is. Okay. And when you're talking of differential forms, what are you really doing? You're working with the tangent space, and then you're looking at wedge products. So the de Rham resolution is closely related to this object there. Okay. And then if you sort of meditate a little more about this, then you see that both sides of this isomorphism are actually computed as the cohomology of literally the same complex. It takes a little bit of reflection to realize that, but now you take that as a given. I'm trying to make my slides look good. And this isomorphism, it's often in its early forms is due to Matsushima Murakami. It's a famous paper in the annals in certain situations where this kind of isomorphism is spelled out. And then, okay. Once you have this Matsushima Murakami isomorphism, you see the relation between the subject of cohomology of arithmetic groups, which is the left-hand side, the cohomology of this locally symmetric space with coefficients in the sheaf, to some cohomology having to do with what? Having to do with functions here, functions on GA mod GQ. These are my automorphic forms of these kind of functions. Okay. And now, I can define what's called cuspidal cohomology. This is, or this was called parabolic cohomology by Shimura, or maybe it goes back to Eichler. Maybe Eichler called it parabolic cohomology in its early form. This is what I'm now going to tell you is one side of the Eichler-Shimura isomorphism. So we got this Matsushima Murakami isomorphism. Let me just rewrite that here. The cohomology of this locally symmetric space with coefficients in the sheaf. This is isomorphic to the relative Lie algebra cohomology of the space of smooth automorphic forms. And that coefficient system, you have to kind of carry that baggage through. Now, inside the space of smooth automorphic forms lives the space of smooth cusp forms. Now you see this diagram from last time. Let me just wait for, there we go. So I got the space of automorphic forms on top there, for which I told you a good reference is Borel and Jacquet's paper in Corvallis. Inside that lives the space of cusp forms. Now I look at some kind of smooth functions in both these spaces. The space of smooth cusp forms is a subspace purely as a function space of the space of automorphic forms. So that inclusion of the space of smooth cusp forms in the space of automorphic forms so this space of cusp forms lives in the space of automorphic forms. A deep theorem of Borel says that this inclusion, in fact, induces an inclusion in cohomology. And so there is some piece here inside the sheaf theoretically defined cohomology group, which as differential forms is represented by smooth cusp forms. So there is by definition some space here. I forgot important qualification for the space, H dot cuspidal. So this is the space of what is called cuspidal cohomology. Please understand there are a lot of technical details I'm just brushing under the carpet. This is just to give you an overview as to how these objects show up, how they're defined. And now, maybe I need more space. So let me just take this to the next page. Okay, I just redrew that diagram there. Let me get rid of cuspidal. And now I told you the space of cusp forms is a direct sum of cuspidal automorphic representations. So this guy here, this is the same. Sorry about that equal sign, or maybe that looks really bad. So this is the direct sum over cuspidal automorphic representations pi of this GK cohomology business affects only the representation at infinity. And the finite part of the representation, there's some level structure to keep track of. This tensor, the GK cohomology of the representation at infinity. And then you have the finite dimensional coefficient system baggage to carry through. You get a decomposition of this kind. And let's ask ourselves a little more about what that space is. There is a Kunneth theorem in place for relatively algebra cohomology, which will tell me that this, you remember G infinity and K infinity all factor over the places at infinity. So this is a sum running over degrees QV, adding up to the dot of the tensor product of HQV, GV, KV, maybe circle, pi V tensor, M mu V, the V and tau you can interchange. And these guys are my discrete series representations. If I were to work with Hilbert modular forms, and they have cohomology in degree 1, and actually only degree 1. And so this QV is, you have no choice but to take it as degree 1. And so each QV equals 1 for discrete series representations. And so this dot, how many QVs do I have? As many as the number of Archimedean places, which is the degree of the extension, D. Okay. So we look at, keeping this in mind, we look at cohomology in degree D of this locally symmetric space. And let me just throw in my, instead of writing just G, the GL2 over F is the group I start with, some level structure, some coefficient system. And inside this cohomology group, there's a, I can look at the cuspidal part of this. So this is what's of interest. Okay. And back, so this is the group, the cohomology group in which all my Hilbert modular forms somehow live. And if I were to remember, I started with the classical world, I talked about the automorphic representation theoretic world, and now I'm talking about the cohomology of locally symmetric spaces. I could have gone, and this is what Eichler Shimura do, directly from the space of weight K cusp forms of some level N and some nebentipus omega tilde. This, there's an isomorphism of this. The easy part is to say that this goes into this GK cohomology. Okay, maybe I don't want to write that GK is just too much to write. So I'll just say it goes into HD cuspidal GL2F KF M mu C tilde. And we have to, so what is the mu with respect to the K? So the K recall was a K1 through KD, or I could write this as K taus, tau running through embeddings of F to C. And each mu is also parameterized by the same taus for Archimedean embeddings of F. And the mu tau, if you work through the details of the construction of discrete series representation and the corresponding finite dimensional, this is what you want. K tau minus 2 by 2, and it's negative. K tau minus 2 by 2. If you know these kind of things, this is actually K for each tau, K minus 2 times half the sum of positive roots. For GL2, which is really this half comma minus half. And these are integral when K is even. So you want to assume, for this dictionary to work, I want to assume all K taus are even mod 2. If all K taus are even mod 2, this is your highest weight. If all the K taus are odd mod 2, then this highest weight looks slightly different. We need not get into it here. And if they have distinct parities, then such a Hilbert modular form will not show up in cohomology. So there are all these parity restrictions on the highest weight coming out of the fact of this lemma here. This lemma, this condition to make the sheaf non-zero, this gives or induces some restrictions on parity. You observe that if this W is, for example, even, then both mu1 and mu2 both have to be, they have to add up to something even. So both are even or both are odd. You see, there is a parity constraint like that, and induces parity constraints. And you will see in Shimura's that paper in Duke, when he talks about special values of L-functions attached to Hilbert modular forms, all is the case. They're all even or all odd. And if there are mixed parity, there are different ways of talking about that mixed parity situation. A fancy way to say is the corresponding Hilbert modular form is not of motivic type, whatever those words convey to you. So there are some parity constraints of this kind, which show up in the game. First comment. Next comment is that there is an action of on everything in sight here, there is an action of K infinity mod K infinity circle. Okay. Acts on the, and what is that? This is just a bunch of products of, forget the central part of it, O2 mod SO2 for every Archimedean place. So the bunch of Z mod 2s, which is acting on the product of Z mod 2s, Z mod 2 to the D acts on all these cohomology groups. So in the Eichler-Shimura isomorphism, there are actually several isomorphisms. I'll just call it theta sub epsilon. For every epsilon, a character of this, the group of connected components, you have to take its isotypic component. And then cut down to that isotypic component, you actually get an isomorphism. So in the classical world of elliptic modular forms, there's just an O2 mod SO2. And you will see in the classical works of Eichler and Shimura, there are two isomorphisms from the space of elliptic modular forms of weight K to H1 D equals 1 and parabolic homology of that modular curve. Okay, I got 5 minutes. And I did say that in my abstract, I'm going to say something about L-functions. So let me just give you an super crash course on how L-functions are viewed in cohomology. So to simplify life, let me just take F equals Q. For a general totally real field, you just need the baggage of a totally real field. And we have fixed an Eichler-Shimura isomorphism between weight K, level N forms, gamma naught N, with now H1 cusp of a locally symmetric space GL2 with gamma naught N level structure and some representation MK, depending on just the integer K and plus or minus, depending on. Okay, if I take a if I take a cusp form here of weight k, and let me call it phi, you look at what's called the Mellin transform of this cusp form. So I look at phi goes to this integral 0 to infinity of phi of iy y to the s minus 1 dy. You stick in the Fourier expansion. Suppose phi of z has some Fourier expansion summation a n e to the 2 pi I n z. Stick that into this integral, interchange summation, integral, and summation, follow your nose, and then you will see that this integral literally becomes 2 pi to the minus s gamma s times summation a n by n to the s. This integral is this. And this is my completed L function. So what I'm trying to say is the completed, so this is completed. I've completed by this gamma factor. This is the finite part and this is the Archimedean part. So the completed L function is a certain integral, 0 to infinity, phi of iy, y to the s minus 1 dy. And it's always better to write this as y to the s dy by y. dy by y is the hard measure on the positive reals, that group. And now, so this is a 1-minute introduction to L functions and the integral representation of L functions. How is this seen in cohomology so that's the final thing. I'll just say that and stop. So I want to talk about the Mellin transform. So what's happening? Well, you got this upper half plane and the real line IR in the upper half plane. And then when you go modulo this discrete subgroup, this kind of closes up on itself and you get this. Let me draw this in another color so that you see so I got the imaginary axis, and that imaginary axis is a line there. You should think of this as coming from an embedding of GL1 and GL2 with a y in GL1 going to the matrix y comma 1. And if I hit y1 on I, this on I is IY. That's giving me my pure imaginary line. So this then gives me, it induces a map from ideals, modular principal ideals, and some open compact. It induces a map at the level of locally symmetric spaces. Let me just call that iota. This inclusion gives me this. This is my this picture. So you want to interpret that integral in a certain way. So what is phi of Iy? So if this phi corresponds to a class, let me just call it theta phi. This phi of Iy is to be interpreted as the pullback of that cohomology class theta phi via the map iota. Where does this live? Theta phi was a cohomology class in GL2, and I pull it back via iota. So this is now a cohomology class in GL1, some suitable space for GL1, and with coefficients in the pullback sheaf. I'm working with cusp forms, and then now there's a little bit of theory to kind of understand and digest. And fact of life, this theta phi is actually represented by a cohomology class with compact supports. It comes out of the fact that it rapidly decays towards infinity. And so now what do I have? I have this space is basically like positive reals. It's a connected, oriented, 0 to infinity is my orientation, connected oriented manifold of dimension 1. So I know that if I look at the first cohomology of such a manifold with compact supports, and let me just say constant coefficients, this is Poincare. This is just isomorphic to complex numbers. You take a compactly supported differential form and you integrate this against an orientation class. That's simply to say I integrate from 0 to infinity of this omega. And you do the same with this with this class. So my integral phi iy y to the put some, you got to put in s equals some particular s naught, which is kind of brushed under the carpet. This is roughly the integral of the pullback of this cohomology class, and then I have to take it down to constant coefficients. So I'll just call that T for technical. I take it down to constant coefficients and I integrate this against an orientation class. And this is a purely sheaf cohomology theoretic interpretation of the Mellin transform. So it turns out that the L value at a half is what you'll be seeing with this integral. So I got a cohomology class on GL2, I pull it back to GL1, it happens to be of compact supports, and then I have to play a small game to push it down to cohomology with constant coefficients, and then I apply Poincare. Okay, this part of my screen is cut off, so this is roughly L half. So this is how one views an L value as coming from a Poincare pairing. This is Poincare here, by the way. Once you have all the details in place, an entire world will open up, because an L value is interpreted as something entirely sheaf theoretic. And once it is sheaf theoretic, well, sheaf cohomology is rationally defined. Poincare pairing is rationally defined. And so if I cut out by some period, somewhere in this game, some periods are going to show up, then I'll live totally in the world of cohomology classes with, instead of complex constant coefficients with C, I can make it Q coefficients. And so you can prove rationality results for these kind of L values. And then you can try to jazz this game up. Instead of rational coefficients, can I have integral coefficients? And then you run into trouble with cohomology with integral coefficients, might have torsion. You want to avoid torsion in cohomology, and so on and so forth. But the starting point is this, that you realize an L value, a Mellin transform of a very transcendentally defined function, as coming as a Poincare pairing in cohomology. Okay, and with that, I will end my talk. Sorry for going 4 minutes overboard. I'm happy to take questions.
Any questions?
Are the quadratic real fields now worked out in detail?
So for, yes, I suppose. In the sense of, make your question a little more precise. So if your question is, if I take my totally real field F to be real quadratic, Q root D for some positive D. Yeah.
Say Q root 2, Q root 3, and then you consider this irreducible gamma there.
There are
some version of.
So now you have to ask a specific question, has a specific question. For example, this kind of rationality result for L values works totally generally for any totally real field. So that's all Shimura. And in some sense, my paper with Naomi Tanabe was just for us to understand Shimura's results viewed from this cohomological perspective, which is also not new. This goes back to Hida and Harder. You can ask question like, okay, I just said torsion in cohomology. So if I take a real quadratic field and just take Z coefficients, what do I know about torsion? I don't know personally, but I would like to say that people would have thought about these things. And if Guhan, you have anything to add, please do.
Yeah, and I know in the imaginary quadratic case, it's been worked out. So I'm pretty sure, totally real, real quadratic should also be done.
But that's
right. So
that goes into Bianchi groups and other things, right?
Yeah.
Exactly.
Yeah.
So I was just going to say some more Bianchi group, I can look at GL2 of O or SL2 O, where O is the ring of integers of Z, which is Zi. Take O as Zi. That was my original SL2 of Zi. What can we say about the cohomology of that? And so this is a kind of parallel stream which also has gone on for several decades. Yeah, I don't know it well enough to say this you can do actually in a real quadratic or imaginary quadratic, which is not yet known in all generality.
Oh, I think it was saying.
Sorry?
No, nothing.
For the quadratic imaginary, probably we can say more because homology of Picard surfaces has been studied quite a lot.
Yeah, that's right.
We know more. So, sorry?
No, that's a Bianchi group, I see.
Yeah. Okay. Any other questions?
So actually, so I have to, maybe I will make one more comment. So Devendra had asked me to talk something about modularity. And so I apologize. I didn't really, it's kind of difficult to get to that stage. Maybe right in the beginning of my first talk, I had said, once you have the object and you have made your peace with one world of this object, maybe the classical world, maybe automorphic representation theoretic world, or this world of cohomology of arithmetic groups, there's actually yet another world. We can, these locally symmetric spaces happen to be the complex points of a variety. In one, we would just say Hilbert modular variety. And instead of the sheaf I just threw at you, there is a related kind of sheaf one could consider. And you can look at the coherent cohomology purely in the algebra geometric world. So that actually is a sort of parallel cohomological world. Once you have these objects in place, then there are all kinds of different questions you can take off into, and one aspect is modularity. Modularity is a generic word to coming out of the Langlands program, that if I had some suitable Galois representation, is it related to modular forms, in the sense that the L function, the art in L function of that Galois representation is the L function of this modular form. That itself is one aspect of an even slightly bigger aspect of the Langlands program, which is modular forms on the one side and what are called motives, some algebra geometric, sometimes even hypothetical object called a motive. A motive is a theory which lives behind various cohomology theories. It has realizations, often three realizations: a Betti, a de Rham, and a L-adic. The L-adic realization of a motive is the Galois representation, but it can have other realizations, and those also play a role. So I'll just quote, there's a famous paper in Inventiones of Richard Taylor, and simultaneously there was also in Inventiones by Blasius and Rogowski, where they construct motives for Hilbert modular forms. And to do so, everything that we just talked about, Bianchi, they do a little base change, and then they go into U3, and then the cohomology of locally symmetric spaces for U3, these are these Picard modular varieties. Those are somehow better understood. And there they cut some piece off in the cohomology, and that magically is the motive. Okay, so there are all these have to be put in place. So there are layers and layers of worlds which open up depending upon where you want to go. So I apologize, I didn't really get to modularity. It's just too difficult. And partly I don't understand it so well. So I just stayed in my comfort zone of just talking about L values and Poincare.
Still wonderful. I sort of have maybe a very naive question, but so can you see the functional equation of this L function is there a cohomological interpretation?
Functional equation of this L function, I will give you an answer which you will like, because if you go back to Manen's paper on this p-adic integration, Jacques Langlands p-adic, whatever it is, 1976 Russian math surveys, where the first time p-adic L functions started getting discussed, there he says one of the big problems is to see if you can prove a functional equation for p-adic L function. And one way to address that is to use something specific for GL2, actually GLN. You see, GLN has a very nice outer automorphism. Namely, matrix G goes to transpose G inverse. Okay, there's an outer automorphism. And there's an old beautiful theorem of Gelfand and Kashda locally, and then therefore applies globally, that if you take an irreducible representation and I pre-compose it by transpose this outer automorphism. So if I have a representation pi and take my new representation to be a G goes to pi of transpose G inverse. This is isomorphic to the dual representation, okay, the contra-gradient representation, which is what you need on the other side of the functional equation.
Right.
The LS pi is related to LS pi dual. And so now you can try to set things up. You have your locally symmetric space, and that outer automorphism induces a map at the level of locally symmetric spaces. And so by functoriality, you will get a map from the cohomology of a space to the cohomology, the same space, but the sheaf has gotten dualized.
Yeah.
And my Hecke module here will get mapped to the Hecke module attached to the dual representation. And then you can try to play this game. So Fabian Januszewski, in some paper of his, addresses the functional equation for p-adic L-functions using this transpose inverse trick.
Okay.
So the answer is yes, you can see it in cohomology, but although one is using a GLN special theorem, that transpose inverse realizes the dual representation.
Okay. Any other questions?
I have one question. So in this relationship with the L function and the SIP cohomology that you mentioned, do you also use the relationship with the SIP cohomology with the relative GK cohomology, that theorem you mentioned about?
Yes. In fact, to make very much. So you will have to, I will ask you to look into this paper of mine with Naomi Tanabe, where these details are worked out. So your question, the answer lives there. How do I make that statement? How do I make that statement precise? On the one hand, I have a cohomology class living in sheaf cohomology and purely maps some cohomological maps. On the other hand, I have some integral and of a cusp form. What is the relation of that cusp form to that cohomology class? And if I want to make that precise, in some sense, this becomes, how do I make Eichler-Shumura precise? You do need relatively algebra cohomology. There's always a playoff. In fact, I don't think you can get to an L value directly without journeying through relatively algebra cohomology. The answer is yes, and very much yes.
I have one more question. This is more naive question, maybe. Using this relationship with the L function and the cohomology, what kind of questions you can answer about the L function? For example, the algebraicity questions probably you can answer using the cohomology. What kind of other kind of questions you can answer?
My own motivation has been algebraicity. The next thing that you can address is congruences, which is again, you have an L function. What do you do with it? Okay, so you have the Riemann zeta function. Now, what do I do with it? You can, first bifurcation is you can go into the analytic theory, prove subconvexity, you want to prove the Riemann hypothesis, or you go into the algebraic theory, so to speak. Zeta 2 is pi squared by 6, zeta 4 is pi to the 4 by whatever. And after algebraicity comes the next layer of questions, which are the Kummer congruences. That if two integers, n and m, are close p-adically, so if n is congruent to m mod some p power, then very beautifully zeta 1 minus n and zeta 1 minus m are close p-adically. So if n and m are congruent mod p to the k, zeta 1 minus n and zeta 1 minus m, I got to tweak them a little, is congruent modulo, I don't know, p to the k minus 1 or something. So these kind of congruences, to prove them in higher generality, the cohomological perspective lends itself very well to the study of congruences, because I can take my sheaf, my finite dimensional representation, I was working with a split group after all, that works over Q, and even better, actually, I can take a Z lattice, which is stable. I look at homogeneous polynomials in two variables with integer coefficients. That's I could take that as a coefficient system. And then I can go mod P or mod P to the K and study the cohomology groups. And I can take the limit of these cohomology groups. And you can do all kinds of things. Okay, so preparing yourself to the study of congruences. This is one answer. As I was saying this, something else occurred to me. There is
maybe the derivative expert.
In a related way, you see the old Ramanujan congruence. Let's go back to Ramanujan's 1916 paper on some arithmetic functions. He said tau p is congruent to p to the 11 plus 1 modulo 691. Okay, boom, somewhere out of the blue, he pulled this out. And there's an interpretation of this by Sayre that this cusp form is congruent on Eisenstein series. The Ramanujan delta function is congruent on Eisenstein series, whose pth Fourier quotient is the p to the 11 plus 1 modulo that prime 691, which is called a congruence prime now for that delta. All this can be seen in the world of cohomology of arithmetic groups. So that 691 appears as the denominator of an cohomology class. It's not cuspidal, it's the kind of complementary on the Eisenstein cohomology class. And Harder has this very nice way of explaining this, of seeing Ramanujan congruence completely in terms of details of H1, upper half plane modulo SL2Z, coefficients in the appropriate sheaf, the 11-dimensional representation, weight 12 cusp form, right? So 11-dimensional representation, and so on. You can make this Ramanujan congruence. You can understand these kind of things. So this is one possible cluster of answers to your question, Naomi.
Just to advertise, like next week in number theory lunch seminar, Harder is going to speak about tau p. Isn't just because of
okay,
this. So,
I want to attend this. Okay, I
Yeah.
still get Max Planck mailing. Okay, if I miss it, I'll request
I
you
will
to
remind
just
you,
forward me the announcement.
Yeah,
Okay, very good.
Also, like about before you mentioned about motifs and L values and then cohomology of arithmetic groups. So there will be a summer school, especially which will in Strasbourg this year about motifs and arithmetic groups in connection to the L function and congruences.
Tell them to invite me. Why am I not invited?
So it is recording, then I will tell you the truth. What before you were supposed to come, but that time we didn't have a funding and this corona was spreading too much. Yeah.
I have some research funds. I could
Yeah.
forcing an invitation publicly.
No.
Last thing a senior
before Harder already decided that he will take if you would have managed to come and this little bit not too far this distance, US and Germany, we were that would have been taken care already. Yeah.
I haven't been to Strasbourg. I would like to come.
So
Guhan
please,
is also
please,
looking. Guhan, have you been to
please.
Strasbourg? Let's go. Yeah, okay. So good to know. When is this exactly in Strasbourg?
It will be June 13 to June 17.
Oh.
So there's a question about the congruences asked. So Neil Damigan will explain this in detail. So yeah.
Oh, good to know. Okay, I'll probably follow long distance. Okay.
Okay. Any other questions? Or if not, let's thank Raghuram for this wonderful talk.
Okay.
Thanks, Professor Raghuram and Guhan,
No
for sharing this talk. See you again sometime in this series, maybe sharing or talking.
Sure, yeah.
Okay, then. Have a good day, Professor Raghuram.
Yeah, thanks. You too. Good night.
Okay.
All right, good night, Kulkarni.
Yes.
Chat. Okay.
Can you stop things?